To the 11 of you that watched my last video, the part 1, I'm sure you guys were waiting so eagerly for the Gauss's law video. But I actually, I recorded that right after I made the first one, and I realized while I was explaining it, I don't think I actually fully understand this. Like, I was in the middle of explaining it in my head, I was thinking, wait, why does this make sense? And I had to, I had to go, not go. I don't really remember that day because it was so long back. But the point is, I had to read about Gauss's law again, try to understand it, try to make it make sense, and now I think I'm ready to explain to you guys why Gauss's law is really useful. So, to recap from the last part 1, for those of you who weren't the 11 people who watched the video, we basically said that electric flux has to do with we use this symbol. I still don't know how to pronounce it. I think it's phi. But it has to do with hey, if you had a sheet of paper, right? And this is kind of a 3D view, but if you had a top view of the paper, and let's say there was an electric field piercing through the sheet of paper, right? Maybe there was a parallel plate that is making this uniform electric field. Then we can sort of conceptually, right? And this is the 3D view passing through. We can kind of, make this relationship between the amount of field lines passing through the sheet of paper, if we had sorry, I lost my train of thought. But what I'm trying to say is, hey, if you had a bigger, a bigger electric field and you want to get more electric flux, hey, you can make the sheet of paper bigger, or you can, increase the amount of you can increase the strength of the electric field so there's more field lines. So we basically said, hey, electric flux, right, with the number of field lines going through that sheet of paper is equal to the electric field times the area. I'll just do vectors. Actually, no, I won't. The electric field times the area of that sheet of paper, right, length times width, or whatever, base times height, or whatever. Electric field times area times cosine theta, right? Because it's the cross product between the area vector, which we said always has perpendicular direction. I should do this in the last video. I should use a different color, which has a direction perpendicular to the field, or to the area, and we say, hey, the angle in between them is how we get the cross product. So obviously the angle 0, hey, cosine 0 is 1, you get the most electric flux when it's flat. Okay, that was kind of a recap of electric flux, but what I kind of hinted at towards the end is, hey, sometimes the electric field is not constant. What if you have, let's say, a proton, right? So you have a proton here has a positive charge of, positive E, right? And we have a sheet of paper, right? This is not a good 3D view. Let's do it like this, right? So the electric field is going to radiate outwards, but guess what? If we drew a top view this time, right? If we drew the top view of the sheet of paper, there's going to be some that's perpendicular, but then there's going to be some that isn't perpendicular, right? Because if you have our charge right here, and then if we think about Coulomb's law, remember, Coulomb's law says the electric field is equal to Q times, or the electric force is equal to Q times the electric field, which is our charge, and then that's equal to 1 over 4 pi epsilon naught, which is a constant, times Q over the distance, or R squared, right? KQ over R squared, or this is the same as the K constant, Coulomb's constant. Anyways, the distance here is bigger because of Pythagorean theorem, so it should have less electric field. We can't just do E times A times cosine theta. We have to do an integral. We have to sum up for this, for this this really small amount of area, dA, there's going to be a certain electric field. And when you integrate it, you would get the electric flux is going to equal the integral, not the closed, did we talk about closed integrals? Okay, whatever. It's going to equal the integral of the electric field times dA, cosine theta, right? And we're doing that cross product once again. And then obviously if you have like a closed surface, so if you boxed this charge up so that it's in a little box, it would be a closed interval, right? Okay, so it would be really, really, really annoying to find the electric flux of this box, right? Because we'd have to take this closed interval. We don't really want to do that. This is where Gauss's law comes in. And to set up Gauss's law, I think we should have a proton here, but instead of a cube, let's actually pick a sphere, and we're going to center the proton at the center of the sphere, right? So it's going to be at the center. So we have a proton, positive E, in terms of its charge, the elementary charge. We're going to make a little sphere. Now, this sphere is imaginary. It's not like an actual sphere, not an actual box, in the last example. It's just an object we're using just to kind of model what I'm about to do here. Doesn't have to necessarily be a real sphere. So if I want to find the electric flux of this sphere, it's right here. Sorry. If I have I hope that didn't get on camera. Oh shit, that's kind of weird. Whatever. If I have a proton here and I want to find the electric flux, obviously we can imagine, right? Everything's going to be radiating outwards, right? Now what's pretty interesting is, okay, well, it's not a sheet of paper. We're going to have to use, and it's not we got to use this equation to figure out the electric flux. We're going to have to take this nasty integral. But what we kind of see is that, well, the electric flux, okay, let's say we want to take this dA. So it's kind of hard to envision because it's a 2D object, but there's going to be a small amount of dA right here on the sphere, right? Because the sphere is like a circle, but 3D. And there's going to be a dA right here, right? Because if you imagine this is like a bubble, there could be something like on there. So dA is all these different dAs. But we know the electric field is equal to this, right? So, the total flux is going to equal, we know that the electric field at this point is going to equal, I'm not going to do the 4 pi E naught stuff yet, I'm just going to say K, Coulomb's constant, but they are the same thing. This is not even the right equation, I'm so sorry. This is the electric, this is really bad. Oh, I should not have done that. I said this was the electric force equation. I'm so sorry. This is the electric field equation. To get the electric force, you need the extra Q. But whatever. Point is, the electric field is going to equal, at this dA, the electric field is going to equal the charge, whatever the charge is, over, KQ over R squared. So, KQ over R squared, well, guess what? For each dA, for each little area on the sphere that we're trying to find, the electric flux for, this R is going to be constant, because it's a sphere, right? Spheres always, like each point on the sphere, each little area is always going to be the same distance away from the center as the other, right? That's just how a sphere is, and because the proton's in the center, the electric field for each little individual point is constant. It's a constant thing for each dA. So what we can do is, because this is constant for every single dA, for every area, and also it's also going to be shooting, the electric field is going to be perpendicular to the sphere, right? Because, if you imagine if you put a proton here, it's not going to accelerate this way or that way. It's going to be completely radially outward. So this cosine theta we can kind of ignore. Cosine 0 is 1. Hey, it's going to be the electric field now times this closed integral. And when you're taking the integral of the total area, that's just the surface area. For a sphere, it's given on your equation sheet. It's 4 pi r squared. So the electric flux is going to equal the electric field at one of these points, at any point r away. In fact, let's substitute that in. It's going to equal KQ q over r squared times 4 pi r squared. And take a look at that. You can even start to see these r's cancel out. The r squareds cancel out. So you're left with, if we take this back here, you're left with the electric flux is going to equal kq times 4 pi. It doesn't matter. We're going to even simplify this further, but it doesn't even matter that the radius, it doesn't matter what the radius of the sphere is, right? Because I said it was an imaginary sphere. This could be the goddamn Earth, right? This could be, I don't know, a baseball. It could be whatever, right? So the radius doesn't matter. Now, that's what mathematically tells us. Well, why does this make sense? Why does the electric flux of piercing outwards of this this little thingamabob, this sphere, why does it not matter on the radius? Well, hey, take a look. If you made the radius like 4 times bigger, well, then at that point, right, the electric field, if it's 2 times bigger, I'll just say 2 times. You can imagine that it's going to be 4 times weaker, right? Because we have r squared in the denominator. If we make our radius 2 times bigger, the whole electric field is now 1/4 as much. It's going to be 4 times weaker, or 1/4 as strong. But when you make the radius 2 times bigger, the area, right, that dA is going to be 4 times bigger, because the surface area is 4 pi r squared. So 2 times the radius, you're increasing your area. We talked about in the last video, how do you increase electric flux? We said, hey, increase your electric field, or make it stronger, or increase the area. So we're increasing the area while the electric field is decreasing. The flux remains the same, because it's the same factor by 4. They both have the r squared relationship. Well, one is inverse and the other is proportional to r squared. Okay, I'm just going to check what time I'm at, because I'm like talking really fast. Okay, 12 minutes. Let's now simplify this even further. We're going to say, okay, k is the same as just 4 pi epsilon naught, and then you can now see, oh my god, oh, and I forgot the q. There's also the q. And remember, this is the q that, this is the electric field. This q is the q that creates that electric field. So this q is referring to the proton's charge. Okay, the 4 pi's cancel out, and we're left with that the electric flux is going to equal q over epsilon naught. Wow, what a result, right? We did not have to do that integral, or at least, a painful one. We could find that, hey, the electric flux is going to equal q over epsilon naught. And in fact, it's going to equal q enclosed, okay? Q enclosed over epsilon naught, because we're dealing with a closed surface, and this is the q inside of it. So this is a pretty cool result. One thing, so why is this useful? Okay, first of all, this means that the electric flux for any enclosed charge is going to equal q enclosed over epsilon naught. It didn't matter that it was a circle. In fact, what you're going to find is if I had the same proton in a cube, right? And I say, okay, this is going to equal the integral of the electric field times dA cosine theta. What I can find is that, okay, the electric flux in this case is going to equal q enclosed over epsilon naught, regardless. Now, it's the same thinking in the sense that, well, if you're doing the integral, this electric field is going to be the closest to, because if you think about a cube, if I draw the top view actually, right? You think about a cube, this is the closest to it, but the corner is farther, but now there's more area. If you carry out the integral, you will probably get the same, you will get the same result. It is always q enclosed over epsilon naught. Always. I could have a weird shape like this, and still using that principle that, okay, this is closer, and this is like a 3D object, and this is a top view or whatever. But hey, this is closer, so there's going to be a stronger electric field. So when you're doing the integral, like this dA is going to have a really high electric field, but then this dA is going to have a really low electric field, but it's like it's farther away than more area. The point is, you would always get Q enclosed over epsilon naught. It always holds. This is a true fact. Like this is always going to be the case. Now, with that said, there are more times. You can choose any shape you want, but you got to choose a shape that's going to help you on the problem. Because let's say we wanted to find, well, for a let's say for a I don't know, for a proton, whatever, or let's do an electron, because they don't get enough love. If we have an electron here and we want to find, well, what's going to be the point? What's going to be the electric field at this point? I don't know, like a distance away. Okay. First of all, I should probably say real quick, this is Gauss's law. This is what Gauss's law is saying. Gauss's law is saying that the total electric flux of an object that's enclosing a charge is going to equal Q enclosed over epsilon naught. This is Gauss's law. Okay? So now, with that in mind, we can actually kind of work backwards. Let's say we're asked, what is the electric field? We could just use Gauss's law. Now, how are we going to use Gauss's law? Well, we're going to say, hey, we got to choose some sort of Gaussian surface. So the Gaussian surface is kind of what I've been talking about, like, hey, this is an imaginary sphere, imaginary cube, doesn't exist, doesn't hurt the problem. That's what we're going to do again, right? It's just kind of a problem-solving strategy almost. It's not really I don't know if Gauss's law is really I don't know if it's like a property of the universe or something like that. Like how I don't know, Newton's third law is. But whatever. My point is we got to choose some sort of surface. We probably want to choose something like a sphere, and the reason we want to choose something like a sphere is then we don't have, for every dA. We talked about it's not centered at all. Pretend this is the center of the sphere. We talked about, hey, for every dA, the electric field is going to be constant. We can take out the electric field. If we did something like a square, so let's say this is the point we want to find the electric field for, then we kind of have to be like, okay, well, this is a distance d, but if we want to figure out the electric field, right, it's going to be this kind of a nasty integral because the electric field is different from the electric field here, and it's not a constant electric field. It would be a much more nasty integral to do, right? Because, what if this is the point, right? What if this is the distance, but then all the distances are different? You can't take out the E. We need symmetry. That's kind of the key point here. So, using Gauss's law, we can say, well, the electric field is constant for each point, and then we're going to still do the integral of dA. Remember, it's radially outward, so cosine theta is 1, theta is 0. Q enclosed, I'm just going to say Q. So we are solving for the electric field. Well, the integral of dA is just the total surface area, 4 pi r squared, which is equal to, now if you solve for E, you get, hey, Q over 4 pi epsilon naught r squared. This is Coulomb's law. We got Coulomb's law from Gauss's law, and we could derive Gauss's law from Coulomb's law. They're really saying the same thing. It's just Gauss was pretty lazy and I guess didn't want to have to go through integrals and stuff. Maybe Coulomb was more into calculus. I don't know. But the point is, they're kind of the same thing. Gauss's law can be really useful sometimes. And I'll talk about some more complicated examples of where Gauss's law saves you so much time compared to just using an integral and doing Coulomb's law. For example, like a rod, right? For like a rod, and you want to find the electric field at this point, well, if this was our x-axis or a y-axis, we have to do like, okay, this is going to be a dE right here, and there's going to be an electric field right here. It's not a point charge, so you can't use this equation. You have to integrate all the dE's and dQ and all that fun stuff. One thing I just want to show you really quickly is be careful of Gauss's law. I had this question myself, and I was like ripping my hair over it, but now it just kind of makes sense. Like Gauss's law is always true, but you just have to be careful with it. Let's say I wanted to find the electric field of like an electric dipole. I think that's how you say it. Dipole, dipole, I don't know. Whatever. This is where you have like a proton right next to an electron, and you want to find, or you know, whatever, positive charge, negative charge that have the same charge, and you want to find, well, what is going to be, so I'll just make that clear, Q, negative Q, and you want to find, well, what's going to be the electric field at this point? I don't know. One thing you might be tempted to do is, okay, let me make, just like I've been doing, let me make a sphere, right here, let me make that sort of sphere, and we'll just say the center's in between them, and they're, I don't know, we can even say they're equidistant from the center, right? This is my Gaussian surface, so according to Gauss's law, right, if we go back to the sphere example, we get that the E over 4 pi r squared, because that's the total surface area of the sphere, is going to equal Q enclosed over epsilon naught. Well, if our Q enclosed of the surface is going to be Q, right, and Q enclosed is like you're adding up all the charges. I forgot to talk about that. So in this case, we would do Q plus negative Q. We're adding up the total charge. Q minus Q, well, that's just 0. So this whole thing becomes 0 over epsilon naught is just 0. 4 pi r squared, well, the electric field has to be 0, right? Because Q enclosed is 0, the electric field has to be 0. But, you know, let's get out of math world, let's go back to physics world. Use your brain a little bit. If this was a point here, you're telling me there's no electric field that would cause any acceleration? There would be, right? You would, if you're a proton, you would start going away from the positive and start accelerating towards the negative, or whatever the case may be. There's definitely an electric field. The thing you have to understand is that when you don't have symmetry, when you don't have any symmetry, you can't use the shortcut version of Gauss's law, where the electric flux is equal to EA, and then EA cosine theta is going to equal, you know, Q over epsilon naught. You can't do that if the electric field is not constant for every point on your electric field, right? Because right here, there's going to be like this D1, it's not an ellipse, but it feels like an ellipse. So there's going to be this D1, D2, and that is going to change depending on where your, you know, area is. Each point has a different electric field. You can't just take out the E, because the E is changing for each dA. You would have to carry out the integral. So Gauss's law is always true. Like if I carried out this integral, it would be the same. Oh, that's a good point. Well, when you carry out the integral for this whole sphere, it would equal 0, right? Because the total flux, if you think about it, right, positive flux is outward, negative flux is inward. There's going to be a lot of positive here, but then there's going to be some negative flux here, and then the whole thing would eventually, like if you carried out the integral, it would sum up to 0. That doesn't mean the electric field is 0 at each point, because there's electric flux here, which means there's electric field here, but there's like that equal amount of electric field canceling it out. Everything would, in theory, cancel out. Yes, because if you imagine the field lines. Yeah, okay. So remember, try to make the physics make sense before just jumping straight into math and be like, oh, Q enclosed equals 0, so the electric field is 0. That's what I was doing, so I hope you don't make the same mistake. I know this is a really long video, and it's during summer vacation. Who does this, right? who learns Gauss's law in the summer? But thank you for watching. I know this was a longer video. Hopefully the 11 viewers will be happy. You can even see my little reflection there.